This is the second lecture of the topic of divergence theorem. We are going to look at a sample calculation of a certain field vector. In this case, we're going to pretend the field vector here as a heat flow Q, which is given by a simple expression here. If you look at this vector, it only has z component, and the z component is actually just a linear function. Now, to remind you again, the idea of learning this is about deep thinking. So you want to start, before even going to the calculation, look at some kind of meaning here. So the statement goes like, if we are given a heat flow Q with this expression through a sphere, then evaluate the left-hand side and the right-hand side of the divergence theorem here. So this is the left-hand side, which is balanced by the right-hand side. Okay. First, try to use your imagination to visualize how this Q looks like. So I'm going to try to sketch the visualization here. We try this. I'm going to draw a axis Z here, and we have it's a Cartesian axis. This is Z, and we have X and Y. And I want to make you see that in the z0 plane, which is simply the xy plane, the value of Q is just 0. Right? And if you look at the way we define the linear function here, it's just a linear function that slowly grows. So you're going to have like a symmetry here. Yeah? One is... I'm going to use different color now. Let's just use a white. So everything now here, let's say at a certain point, it will point to upwards, everything, yeah? And as you go along the plane of z, it will increase in the magnitude. Okay, linearly. The same goes to the negative z-axis. Yeah, you get color here. So it goes like this. So you imagine now, if there is a sphere here, we try to, let's say this is this cross section on z0 axis, and then the whole 3D sphere like that. Now the objective is to calculate the flux. This whole thing here is what we call flux, meaning you need to find the normal component of Q on the surface of the sphere and then integrate, i.e. sum up. Now as you can see, we're going to look at the left-hand side. If you look at the ingredients here, there are a lot of stuff here to be resolved. We're going to look first at the normal, and to be more precise, this is what we call the unit normal. Let's start with this, define this unit normal. First, we have to be specific with the sphere. We're going to say this is a sphere of radius equals to 3. Now, so the equation for the sphere is simply x squared plus y squared plus z squared equals to the radius squared. Now, there are different ways to find the normal vector of the surface of this function. I just want to show you an approach that is quite easy to understand, or to do. So first, we just bring everything to the left-hand side here. So you get like, so I'm going to rewrite this. It's going to be like c squared plus x squared plus y squared minus 9 equals to 0. And then I'm going to call this whole expression as g of x, y, z. So that the normal vector is simply the gradient of g, which is, write it like this, the x component is partial g partial x, 2x here. And then you have partial y, partial g partial y, so 2y. And then partial g partial over partial z, then you have 2z. You can, of course, factor out the constant. Just simply 2 times x, y, z. Which now, as you can see here, makes sense. If you have a sphere, whatever position vector on the surface is just given by these equal values here to point along the radial distance here. So it's equal. Now how do we get the unit normal? Unit normal is just simply the normal vector divided by its magnitude. Okay. Let me write first the 2 times x, y, z, and then the magnitude is simply square root of this whole expression here, which is 4 x squared plus y squared plus z squared. Now you know that we have something on the top here, the normal vector. The denominator is just simply 2, and square root of this whole thing is just r squared, which we are given as 3. So this simply goes to 3, and you have this whole thing divided by 6. So this is where you get the unit vector to be 1/3 of z. So let's resolve the unit normal vector. The next step, if you think about the surface integral of this whole bunch here, this is n df. We know now the unit normal, we're given q. We have to decide on the coordinate system. Because we are dealing with a sphere, it's very natural to use spherical coordinates. So instead of x, y, z, we need to transform this into rho. This is the radial component, and then theta, and phi. This is where it's good to go back to your advanced engineering calculus course and recall back how to use this transformation scheme. So we have the coordinates. In terms of the ds, this is, again, it can be derived, but I'm just going to state the conversion formula, which is given by rho square sine phi dA. You see now we have a conversion between ds and dA. If you recall, ds is a tiny surface in 3D, which is projected to the flat face of dA here. So this is not very correct, but you can get the imagination right. Okay, this is ds projected to dA by this relationship. So now we have to think about, so dA is d phi times d theta. Now we have the transformation. Next one. This is where you need to think in a more careful manner how to define the limits of integration. So let's look at some reasoning here. Okay, I'm going to draw again a sketch of my spherical coordinates, just part of it. Okay. This is the Cartesian part, x, y, and z. Now suppose I have my tiny surface somewhere here. Okay, from the origin here. This is where you need to see how we can get the limit. In this case, we have to deal with theta and phi. This is phi, and theta revolves around z. Now you can see the trace here. If we can get phi here, we revolve around the y-axis, so you get this. This is one slice of the arc of the sphere. Now if I am here, for the other limit, if I revolve around z, then I'm capturing, see now here, I'm capturing the whole domain of the sphere. Let me just roughly so pretend this is a sphere. So that means one is for phi, it goes from 0 to this half of the revolution, 0 to pi, and for theta it goes complete revolution, so from 0 to 2 pi. This is the limit of integration that we will use. We get everything now. We rewrite this again. This double integral of q n hat ds. Now I'm going to call this is what I call flux over this surface. Flux of q. So you have to reread the explanation in the book how this term flux can have different meaning in calculus or in different disciplines of physics. So you can just now resolve this. Q is 0, 0, 2/9 of z, which is in terms of the spherical coordinate, it's 0, 0, 2/9 times 3 cosine phi, and the unit normal vector is, I want to write this without conversion, 1/3 of x, 1/3 of y, and this is where it's, I'm going to convert this because the multiplication of these two components will get to 0, so we are just concerned with the last component here, the z component, which is it's 1/3 of 3 cosine theta, so it's cosine not theta, phi. Where now we get the dot product to be simply 2/3 cosine square phi. Now it's just a matter of collecting all these data to perform the integration. And I want to now give a symbol to this, which is I have in my book. So just have some kind of abbreviation. So we have the first integral and the second integral, and then this whole expression. Now first it's 2/3 of cosine square phi, and then the ds there, I think I have the well, if you work out the arithmetic, should be 9 here, and then sine phi, d phi, and d theta. Now as we did it before, the limit of integration for phi is from 0 to pi, and for theta is from 0 to 2 pi. Now the subsequent step is just to resolve this not so direct integral. Now to do that, you may want to review your EUM 114, or if you want to do it quickly, you can just use some tool that is available. For example, this side. You can just write down here some part of the integration. So as you can look at here, I'm resolving the cosine terms. The constant can be factored out. So the cosine term is the sine and cosine square. So that's what I did here. Sine times cosine square, and I give the limit. This is for pi, 0 to pi. Then you just click on this and then it will give you the answer. The nice thing about this is it gives you the step-by-step process. But you should know this by now. What we want is simply this final number here, 2/3. Now if you work on this, then the other integral is very simple because now theta is just 1 here. So evaluation of that will just give you 2 pi. And then you have this factor. This should come out to be 8 pi. So we have found the evaluation of the surface integral, 8 pi. Okay, now for the left hand side we have 8 pi. Then now we're going to resolve the right hand side. The right hand side is, it would be more convenient for us here because first let's look at the, it's just a triple. It looks more because now you're dealing with triple integral but over some volume here. But what you are dealing here is, as the integrand, is the divergence of Q. Which is, given our simple vector function, is simply a constant, 2,9. So you're basically integrating a constant here. And now it's just a matter of, again, the coordinate transformation. We did that before with spherical coordinates. And the dv is, it's rho square sine phi. Then you have d rho, d phi, and d theta. Since rho is related to the radius, so the innermost integral here, which relates to rho, would be, so before this, it's just like before, so we have 0 to 2 pi, and 0 to pi. Then here is simply 0 to 3. Then I'm going to use this, 2/9, is where the divergence is, and dv is whole expression here. Sine theta pi, again d rho, d phi, d theta. So this again, the quantity that we define as the flux of Q. And by right, it should be 8 pi. So for this triple integral, it's very fast because the limit is clear, and then we just deal with simple expression for the integrand here. So we spend a lot on the calculations aspect, but more important is to observe the result of this calculation. So you can see now the flux is 8 pi, which is positive. Yeah, it's a positive number. The way we interpret this is that if we have a solid surface like this, in this case a sphere, and we define the normal vector to point out of the surface, as you can see from the flux component here, because the way we define is a 0 at the middle of the sphere, and then it goes out of the sphere surface. So going out in the same direction as the normal vector, we interpret this as a flux going out. So you can see this in a sense of like an energy flow out of the surface. Okay, that is one interpretation of the number here. And by convention, we define the null vector out or away from the origin. That's it for the look at the simple example of the calculation involving divergence theorem. See you next time.